So we can divide the whole set of numbers into two categories: real numbers and complex numbers. Real numbers can further be divided into rational numbers and irrational numbers. And rational numbers have a subset, integers, and integers have a subset, whole numbers, and whole numbers have a subset, natural numbers. So every natural number is a whole number. The vice versa is not true. Every whole number is an integer. Every integer is an irrational number. Integer is not irrational. Okay. And no number can be both rational and irrational. And coming to complex numbers, I told you that a plus ib, any number which can be expressed in the form of a plus ib, where a and b are real numbers, is a complex number. And when you take this number, a is called the real part of the complex number and ib is called the imaginary part. And coming to complex numbers, we have something called conjugate complex number. Given a complex number a plus ib, a minus ib is called complex conjugate number. And something which we can note about this, say, okay, let's represent this by symbol z. Z is equal to a plus ib. The conjugate is represented by z bar. So z bar is equal to a minus ib is called a conjugate complex number. Something which we can note with this is sum of a number and its conjugate is a real number. The imaginary part is 0. The difference of a real number and its conjugate is a purely imaginary number. There is no real part. The real part is 0. And a product of a complex number and its conjugate is square, which is a perfect number. Let's see how. Product is a plus ib into a minus ib. We expand, we get a into a square minus iab, product of these two, plus iab, and ib into minus ib. So minus I square b square. I square is nothing but minus 1 minus turns out to be plus 1, and these two get cancelled, so it's a square plus b square, which is a purely real number. And next we will look into fractions. So I told you rational number is any number which can be expressed in the form of p by q. So that's something which we call as fractions. And we have a fraction is called a decimal fraction when the denominator is a power of 10. So 2 by 10, 3 by 10 square, or 7 by, say, 1 followed by 5, 0 is nothing but 10 power 5. These are decimal fractions. And any fraction whose denominator is not a power of 10 is called a vulgar fraction. Say 2 by 3 minus 5 by 7, say 4 by 5. All these are vulgar fractions. And then we have something called a mixed fraction. Mixed fraction is something like a, b by c. So we say 1 1/2, 4 1/3. So things like this are mixed fractions. A mixed fraction is nothing but a plus b by c. 1 plus 1 by 2. 4 plus 1 by 3. When we have a mixed fraction, we need to convert into a perfect fraction. Say something which is the form p by q is called a perfect fraction or a regular fraction, and this is an improper fraction. So to convert this, what we can do is, suppose we have 4 plus 1 by 3. We multiply and divide with the denominator of this fraction here. So we say 12 by 3 plus 1 by 3, which is nothing but 13 by 3. And coming to integers, we have something called parity. Parity of an integer is nothing but its oddness or evenness. Any number which is divisible by 2, any integer which is divisible by 2 is called an even number, and other integers are called odd numbers. So 2 is an even number, minus 4 is an even number, and 6 is an even number. 3 is an odd number, minus 7 is an odd number, minus 11 is an odd number, 99 is an odd number. So something which we need to, some interesting points here are the sum of two even numbers is always an even number. Sum of two odd numbers is always an odd number. Sum of an even number and an odd number is always an odd number. And coming to products, product of two even numbers is an even number. Product of two odd numbers is always an odd number. And product of an even number and an odd number is always an even number. Next we'll discuss about Fibonacci numbers. So this is actually a sequence. Let us say we have a sequence of numbers A1, A2, A3, so on, An. And this sequence is said to be a Fibonacci sequence if we have a recursive formula like this. If n plus 2th term is sum of nth term and n plus 1th term, this is called a Fibonacci sequence. An example of a Fibonacci sequence is, let's say we'll start with 1, 1. Sum of these two is 2, sum of these two is 3, sum of these two 5, and then 8, sum of 5 and 8, 13, and then 21, so on. This is an example of Fibonacci sequence. And some interesting points to note about Fibonacci sequence is the sum of n terms of a Fibonacci sequence is equal to the n plus 2th term of the sequence minus the second term of the sequence. And I would like to introduce or recollect a notation for summation. This is sigma ai, I running from 1 to n. So this is a symbol for summation. And a similar symbol for multiplication is pi. Pi ai, where I runs from 1 to n. This is nothing but a1 into a2 into so on till an, or in sum. And another interesting fact about Fibonacci sequence is an square plus an plus 1 square is equal to a to n plus 1. And another interesting fact is, let us say we have 4 consecutive Fibonacci numbers A, B, C, and D. Given that these 4 are consecutive terms of a Fibonacci sequence, then we have C square minus B square is nothing but A into D. And if you have enthusiasm, I suggest you prove these 3 things that you can take as an exercise. And now, another topic is a factorial. Say, if n is an integer, we have something called n factorial, which is nothing but 1 into 2 into so on into n. So product of the first n natural numbers is called n factorial. So 1 factorial is 1, 2 factorial is 1 into 2 is 2, 3 factorial is 1 into 2 into 3 is 6, and so on. And by definition, 0 factorial is 1. And one obvious thing which we can state is n factorial is nothing but n minus 1 factorial into n. And factorial is defined only for whole numbers, 0, 1, and other counting numbers.